I'm very happy to be here, and thanks a lot for organizing this workshop and for everything. I'm having a lot of fun. So since we already had a lot of Equivariant talks and TMF talks, now it's a perfect time to do an Equivariant computation of TMF. And following Jeremy's talk, I'm going to give a subtitle, a biased computation, suggested by Hannah. Because our focus here is not to compute TMF, which is already computed by a bunch of authors already. Our focus here is to play around with some C3 computations and tested some C3 techniques in this example of TMF. And this project is joined with Jeremy Han, who's in the audience, Andy Sanger, who's on the job market, and Adela Zhang, who's in Copenhagen as a postdoc now. Okay, so I'm going to start with some introduction. Although it's not necessary, it's good to know what you are computing. We are computing topological modular forms, which has thankfully introduced by Leonard. But let's quickly refresh our memories. This connective topological modular form is constructed or defined by Hopkins-Miller as an infinity ring, by Gross-Hopkins as an infinity ring, and then Lurie in modern language. So roughly, you have this moduli set of elliptic curves, and you do the Lee-Mumford compactification, and there is a sheaf of infinity ring spectra on it, and then you take the connective cover, and then you take a global section, and then you take the connective cover. That's the lowercase little TMF. You also have the periodic version and the non-connective, non-periodic version to distinguish between. So the gadget we are computing is topological form with level 2 structure. It is constructed similarly as above, but you want your elliptic curves to have a fixed level 2 structure. And then there is this GL2, ZMAL2, which is the group, symmetric group of 3 letters acting on TMF. And Vesna, in her paper, okay, it stopped working. Gave that if you invert 2n, then you get the equivalence of this non-equivariant TMF with the homotopy fixed point of this TMF with level structure. So if we take n to be 2, we get that apart from the 2 primary parts, apart from the 2 torsions, the homotopy group of TMF can be recovered from computing sigma 3 homotopy fixed point of this TMF2. And for simplicity, we define this to be a genuine sigma 3 spectrum by taking the connective cover of the Borel completion, which is the spectrum on the right. And computation of it has been done by using elliptic spectral sequences. And we also know that away from 2 and 3, there is an isomorphism of pi star TMF to modular forms. And TMF does not have any torsions greater than 2 or 3. So apart from 2 and 3, we know everything. And at prime 2, there are a lot of computations. But today, we are focusing at prime 3. And prime 3, it's also been computed via relative Adam spectral sequence by Hill and Henricus. And there's also a paper documenting the Adam spectral sequence computation by Dominic Culver, and there's also homotopy fixed point spectral sequence approach by these authors. And all methods here mentioned, they require some input either from the Adam spectral sequence of spheres or use total brackets, so more complicated, more involved topological input. And the approach I'm going to use today is the following. So recall we had this isomorphism of homotopy groups of this equivariant homotopy group and this non-equivariant homotopy group. And we can, because we are focusing on the 3 primary part, we can first take the C3 fixed point and then take the C2 fixed point this way. And we are going to use a relative C3 relative Adam spectral sequence, not compared to this. This is non-equivariant relative. We are using C3 relative Adam spectral sequence to compute this. And then taking C2 fixed point, we can get everything. And in our approach, all differentials come from sort of algebraic data, either from Deuce-Stingray algebra or from studying some chains of representations. Okay, so let me give some setup and or refresh some equivariant foundations. So for equivariant spectrum, we have ROG-graded homotopy groups. Namely, for a real G representation, we use pi v to denote the map from SV to your spectrum. And you can also suppress the notation this way. And if G is C2, we have two representations. One is the trivial representation, and the other is the sign representation. And they span ROC2. And when G is C3, there is the trivial representation, and there is a two-dimensional rotation representation, which we'll denote by lambda, and they span ROC3. And to compute HF star underline, you just need to compute via this method, namely some non-equivariant cohomology or homology of some spaces. And the answer, we've seen this left side picture in Clover's talk, I believe. But my grading is slightly different from hers. She used motivic grading. And here I'm using just the number of trivial representations plus the number of sign representations. And the answer here is that you have a polynomial algebra here with A sigma, the Euler class, and U sigma, the orientation class. And then you have a negative cone here, which comes from the Tate. There is a cone point in this degree, and it's divisible by everything in the positive cone. And for HF3, the picture actually is quite similar. And the trick is to take the unit twice the length of the unit of lambda, twice the length of the unit of the trivial representation. Then you get a sort of a sub-picture of the left. So now you have a Euler class for lambda, an orientation class for lambda, and then there is an exterior class here. And you also have a negative cone point. Everything is divisible by everything here. Okay. And now I want to sort of fill up the right picture so that it looks like the picture on the left. So I'm going to introduce this new grading, not me, but people doing these computations, the spoke grading. So S spoke, the sphere, is the cofiber of C3 plus to S0, which is this picture, and that's the egg beater in Clover's talk. And the spinel y-hat dual of it, we denote by S negative sigma, S negative spoke. That's by spinel y-hat duality, you can also write it in a cofiber sequence. And we write it as S negative spoke because of this observation that S lambda smashed with S negative spoke is equivalent to S spoke. So in this sense, we can think of spoke as half of lambda. But this analogy is not precise because if you actually smash the two S spoke together, or a shift of this, you do not get S lambda, or a shift of this, but you have a shift of this. Sorry, you have an S0 plus a free cell. And this is true in general that you can take the cofiber for any group Cn, and you can also call that spoke. If you smash two S spoke like this together, you get S0, and then you get a bunch of copies of Cn plus. And how many copies? You do an algebra. Here you have n minus 1 square elements, and minus 1 divided by n. This is n minus 2. So this is true in general. Okay, so now I'm also introducing this spoke into the grading. I'm calling it pi fancy star. And the fancy star, I'm going to write it as m plus n spoke, where we understand two spoke as lambda. So precisely this way. And this spoke is the C3 analog of sigma, because if you work with C2, then S spoke is just as sigma. And some features of it is that now we have suspension isomorphism only for ROC3 spheres, but we cannot suspend by spoke spheres. It's not an isomorphism. And we can also define ring structure with some care. So if X is a ring spectrum, then this spoke graded homotopy group is a graded ring more transfer in the sense that if I have two spoke-graded, genuinely spoke-graded elements, I can tensor them together as I would for an ordinary ROG homotopy group. But then this is equivalent to a sum of two things, and I'm just picking this representation cell, and that's a product of AB. And filling this spoke grading in, the homotopy group of the spoke graded homotopy group of the coefficient F3, the black dots were from the original picture, but now we have these blue dots filling in the odd dimensions, and we call this A spoke, this U spoke, and the ring structure becomes A lambda equals to A spoke square. This epsilon, which is exterior, equals to A spoke U spoke, and there's no relation here. U spoke square is 0. And we also have this, because there's no spoke-graded suspension isomorphism, so we also document this, the homotopy groups for this. And this, we have a similar picture as we would have thought on the left, a shift of it. But we also have some diagonal elements here from the free cell. And these we will call transfer elements, and later I'm going to mention computation mod transfer, which I mean mod these elements. Okay, so now I'm going to explain some results on equivariant dual-stingral algebra to elaborate on why C3 behaves somewhat differently than C2. So as before, as always, we wrote H star, A star for the pair of dual-stingral algebra, and now we have a structure of a Hopf algebroid, and Hu-Krisch computed the Hopf algebroid for P equals to 2 and the group C2, and it has this form. So the precise form is not that relevant. There are generators Xi I tau j, and Xi I and tau j's are lists of the non-equivariant elements zeta i's plus 1s and zeta I squares. So if you know non-equivariant dual-stingral algebra well, the non-equivariant dual-stingral algebra at P equals to 2 is a polynomial on this generator. But when you lift to equivariant, you have two sequence of generators lifting elements and their squares, and there is a relation between them. The same paper also computes the homology of BPR as a sub of A star, and these computations are one of the starting points of HHR's computation. And as non-equivariantly in this case, the dual-stingral algebra is a sum of copies of H star, and by Clover's theorem, we then get that the A is equivalent to a wedge of suspensions of the Ellenberg-MacLane, just like where you have non-equivariantly for every prime. So equivariantly for odd P, we need some setup to explain what's the dual-stingral algebra. So there is an important H module HT showing up, which is the cofiber of S lambda mapping to S2, and then we desuspend twice. So what is this map? This map is actually the negative cone point, and it's a map that wraps this sphere P times around this sphere, which is non-equivariantly order P and equivariantly non-trivial. And we also have a non-split cofiber sequence writing this HT using the spoke suspension of H. And I'm going to denote the homology of this as M, and so the homotopy of this as M, so the homotopy of this is a suspension of it. You see this from the picture. This picture is a homotopy group of HT, which you can get by computing this cofiber sequence. So you have two pair of trapezoids, and one of them is M, and the other is the sigma M. And on homotopy groups, you have this cofiber sequence has no differential, but it doesn't mean this splits. And in a paper by Sanker-Wilson, they proved that the dual-stingral algebra CP equivariantly is a spectrum like this. So you have the Bochstein, and then you have smash over H for I greater or equal to 1 of a big chunk of spectrum, and the big chunk is sort of has a polynomial generator here, and then this xi is a wedge of HTs together with some element McLean. So the degrees here for this shift and this shift, the cos I and the theta I, are listed as below. And in a paper, so if you look at this, they study the homotopy group of HT, they deduce, and you can see that A star is not a flat H star module like you always do before. And in a paper with Hu, Krish, and Sonberg, we find dual-stingral elements. And these dual-stingral elements can be related to this expression as this way. So we remember the homotopy of HT splits as 2 copies of M's. So then you have, we find basis, generating basis for these homotopy elements, like here. So there is cos I underlying in this degree, and that's a lift of the non-equivariant cos I. And there's theta i's in this degree, and they're actually the norm of the non-equivariant cos i's, and they are lifts of cos I to the p. And there are relations between them as well. Let me give a detour about what we also do in that paper. So using these elements, we found the basis for dual-stingral algebra. And it's not as simple as you just put the products of all elements together, because if you smash 2 HT together, what you get is a copy of HT and then a suspended copy of HT. So like this picture, you have 2 copies of M. So now you want to figure out what are these elements. And there was some trick which we have not figured out why, but it worked, which is you put some formal notation that you let d cos I hat to equal to cos I underline and d tau I hat to equal to tau I underline, and the Leibniz rule. Then you can write, there is a way to write down all these shifts, basis for that using this notation. Okay, so now ending the detour and coming back to computation, let me motivate relative atom spectral sequence from the atom spectral sequence that we are familiar with. So we can understand the atom spectral sequence as a descent spectral sequence in the following way. From the map from the sphere to HF, you can construct this co-simplicial resolution of S. And then you can use dot-com to have a coherent co-chain complex. And this will produce a spectral sequence converging to the completed homotopy group of the sphere. And if you compute this, it's actually the X group of this Hopf algebra pair. So this is the ordinary atom spectral sequence that we are familiar with. And now we consider the map from equivariant TMF to the C3 element McLean, constant Mackey-Functor element McLean spectrum HF3 by taking the first Postnikov truncation and then modding out by 3. This is a map of E-infinity rings. We can form this co-simplicial resolution along this map. And this, by taking homotopy groups and then a homology of the corresponding co-chain complex, we get a spectral sequence which we call relative atom spectral sequence, whose E2 term is the homology of this and converging to the homotopy group of TMF2. And this kind of spectral sequences have been used earlier in C2 equivariant computations by Li Shi, Wang Xu on this C2 BPR mapping to HF2, and they used this to compute all slice differentials for BPR. It turns out there's a match of differentials here and differentials there. And also by Han and Wilson, where they considered the norm of HF2 to HF2, and they showed that the norm of HF2 is Borel complete by analyzing the spectral sequence. So now back to our problem. We have a spectral sequence, how to compute the E2 term. Well, this turns out to be non-trivial because usually we hope to be able to compute E2 as some X groups like before. But here, our input pair here, this is a Hopf algebroid, which is okay because there is trick for this kind of situations, usually you just filter the E1 term, then you will have an associated graded being a half algebra, and then you can compute the E2 page as an X that way. And then you do some algebraic Box-size spectral sequence to recover the E2 term. That's okay, but it's only a half algebroid mod transfer. The mod transfer, I mean, in the computation, there are some A-spoke torsion things or U lambda periodic things. And it turns out that we cannot throw them away. If you throw them away, you get a significant discrepancy with the homotopy group of TMF. So we should treat these transfer parts with care as well. So what we do is that we first do the mod transfer calculation, and then we can deduce what's happening altogether here from the mod transfer calculation via something we call the evil-good sequence. And then, now we get an E2 term, so the last step is to compute the relative atom spectral sequence. Okay, so this is a summary of what the roadmap using a diagram. We have this relative atom spectral sequence, and we filter it so we have an algebraic A-spoke Box-size sequence to compute. And then, to compute this part, we have the mod transfer part, which we call good, and we have the trans part, which we call evil, and there is this evil-good sequence. And how do we deduce this? It turns out that there is a third coherent spectral sequence here, and we know precisely what it converges to, and we know this also happens for these two parts as well, the evil and good. We know what they converge to via the coherent spectral sequence. So using this, we can deduce this part. And then we work with the left square. Okay, so some remark is that we use spoke grading, but we end up with restricting to our C3 grading starting here. But the spoke grading is extremely convenient to compute this part. And also, we are implicitly taking Borel completion, which is equivalent to inverting U lambda in the computation. And sometimes I did not write U lambda inverted, but that's implied. That's because we don't want to treat with the negative cone of all the computation. Okay, so now first step, what's the relative dual stingray algebra, or what's the half algebraic pair that I promised to you? Let's deduce that. So in Vesna's paper, she gave the non-equivariant homotopy group of TMF2. It's a polynomial on two generators of degree 4, and C3 acts here as a reduced regular representation. So you can compute this via some tour that the relative dual stingray algebra is exterior on two generators of degree 5, and mod 3, you have exterior F3, and then you have a tau 0. And in Dylan's thesis, he constructed a C3 equivariant map from this spoke representation 2 rho minus 1 minus spoke to TMF2, whose underlying map hits precisely this lambda 1 and lambda 2. So this homotopy group at this degree 4 is realized by an equivariant map. How do we see this as degree 4? Well, you can think of the spoke underlyingly is degree 1, two spheres of degree 1. So this is 6 minus 1 minus 1, degree 4. And then you can construct from this C3 equivariant maps from S2 rho minus spoke to this relative dual stingray algebra, whose underlying will hit the sigma lambda 1 and sigma lambda 2. And you can also use the E-infinity structure here, tensor two maps together, and you get a map from the sphere 4 rho minus lambda into this. And it turns out that using this map, we get a map from the right side to the left, and it's an equivalence of C3 spectra. So modding out by 3, you get a description of the relative dual stingray algebra as some spoke suspensions of the HF3. And then you can compute the homotopy group by that of the right-hand side. So you have the tau 1 mu3, and you have the y. And this tau 1 mu3 is in some spoke grading, 2 rho minus spoke. This y is in degree 4 rho minus lambda. And there's also this transfer elements. And modding out by transfer from construction, we can tell tau1 mu 3 squared is y. So if we mod transfers, so throw all these away and using this relation, we get this is coefficient and exterior tau 0 and polynomial generator tau1 mu 3 mod the relation that tau1 mu 3 cubed is 0. We have tau1 mu 3 squared, which is y, and tau1 mu 3 cubed is 0. So that's how slope grading helps, because it makes it simple like this. And now here's some flatness issue that one has to consider for atom spectral sequence computation. So I said this is a half algebraic because we have this eta L, eta R, and psi from map of spectrum. However, to get a map on their coefficients, you need that if you take homotopy groups here, it should be the tensor of their homotopy groups. But this is not the case for us. But it's okay. So it is an isomorphism if you mod transfer. So modding out by transfer, you do have a half algebraic pair. Okay, so now modding out by transfers, this is the half algebraic pair we get, and the data is the following. The right unit of U spoke is U spoke plus tau 0 A spoke, and the right unit of U lambda is U lambda plus tau 1 mu 3 times A spoke to the fifth, and the tau 0, tau 1 mu 3, they are primitive. And how did we get this? We use this map from C3 equivariant Dirichlet algebra to this relative Dirichlet algebra. And on the left side, we already computed in an earlier paper, as I mentioned. And in that paper, we got these elements, and the relevant ones are this Cauchy-1 underline, Cauchy-1 hat, and there's right unit formula for them. And we know that the map, well, we deduced that the map on the previous page sends these elements in the Dirichlet algebra to these elements in the relative Dirichlet algebra. So you can plug this in the formula and deduce this eta R formulas. And similarly, you deduce this coproduct using the coproduct known in the Dirichlet algebra. So now we know this, and the consequence is that there are all A spoke powers here. So if you mod out by A spoke, and if you filter by A spoke, then it becomes eta R is equal to eta L. Then we get a half algebra mod transfer, and so we modify it so that so that eta R equals to eta L, and then we compute homology of that instead. That's the E1 page of an algebraic A spoke spectral Bach-Stein spectral sequence, which will converge to the E2 term that we want to compute. Okay. So now let's think about the transfer elements. We throw them away in the previous slide. So how do we get them back? Well, in the chain complex, A spoke filter co-chain complex, we can take out all the transfer elements as a sub, and the quotient we call it. The sub we call it evil, the quotient we call it good. And you can compute homology of these parts. You will get a long exact sequence of homology groups. And we call this long exact sequence evil good sequence, or this Agatha-logical sequence motivated by the work of these authors. And if you want a more precise definition, an evil element or a transfer element is precisely the A spoke torsion element. So we have established this part of the roadmap, I promised. So now, actually, we should do it from start to end, but actually this part is really easy. Let me explain. So the E1 of the good part, or the E1 page of the algebraic A spoke Bach-Stein sequence for the good part is an X, because we have made it so. And it's an X over this algebra, which by algebra you can compute. It's this. It's not important what precisely they are. The point is that it's easily computable. And these are cycles given by these classes. And the algebraic A-spole Box-Stein sequence is completely algebraic. So you just deduce it from the right unit formula. We had this for U spoke and U lambda, and we also can multiply it to square this expression, we get this. And from this left side, we deduce algebraic A-spoke differentials D1, D5, and D10. So these are all the differentials in the good part of the algebraic A-spoke Box-Stein spectral sequence. The evil part, we don't know what it is yet, but they don't participate because they are all simple A-spoke torsions. So if you filter by A-spoke, then there's no way they're in different filtrations. Okay, so now we are heading back to the right side, the evil-good sequence. How do we compute the evil part? Well, let's see why the evil part is evil. The evil part means the free part, right? And it's relevant because in this expression, you have this full-graded sphere. And if you smash two full-graded spheres together, you get this free cell. And then if you smash further from free cell, you always get free cells. So you get this subcomplex of free cells. But there's a way to work with them, which is if you consider the underlying homotopy group of this as a C3 representation, you end up replacing this by a reduced regular representation and replacing this by a trivial representation. And this trivial representation is actually sim2 of this reduced, exterior 2, lambda 2 of this rho bar. So we can write it this way. And this expression on homotopy groups matches with this expression very well, because if you tensor to reduce regular together, you get 1 plus rho, which is precisely what this is if you translate to their underlying homotopy groups. So it happens that if you take the underlying homotopy group, you do get this isomorphism. So we replace the co-simplicial, the coherent cochain complex by its underlying homotopy group. We get this coherent cochain complex of C3 representations, and we can recover the homotopy group of the Borel completion of your coherent cochain complex, because that's just the group cohomology of this cochain complex, and then you add a U lambda plus or minus like this. Right, so this was the C bullet I was replacing my Adams resolution with. And we want to compute this thing, which is its HC3, its homotopy fixed point. And this is a coherent cochain complex, you can also realize it. And there is this spectral sequence of coherent cochain complexes that converges to the realization. So that's the third spectral sequence, like this. And this is the E2 term for that spectral sequence. And this, we mentioned it because it's actually easy to compute. It's just the homology of the coherent cochain complex. And then you take the group cohomology. And this coherent cochain complex, it was a symmetric. So it's the free tensor algebra on these representations. And its homology is a symmetric algebra on these representations. So we can plug in the answer into this spot. Okay, and now this can be filled in as a diagram. So there is a spectral sequence here as well, which makes it a diagram of spectral sequences. So we need to use some synthetic language. We had this filtration, the Adams filtrations. We also filter by the Whitehead filtration. Then we have a bifiltered spectrum. with 2 directions. Then we have a trigraded homotopy group, and we can fill in this as a tau-inverted tau-Bochstein spectral sequence for the delta inverted unit in this category. Okay, so it's not important what I just said. The important thing is that we have this diagram of spectral sequences, and there's synthetic interpretation of all these spectral sequences in this diagram. Okay, so I've established this square, and now I want to, and I'll also explain how to do this. Now I want to show how to do the right part. So the right part, this is the middle thing, is this spectral sequence we want to compute. And the evil and the good, their abutment sits in a long exact sequence of homotopy groups, which was the evil-good sequence. And their E2 term, they all have spectral sequences converging to their homotopy groups. And we know what's the answer here, and we want to deduce this part and this part maybe. Sorry, we want to deduce this part and this part, so that's the most important. But to do this, we need to know this. Okay, so the right side is easy. It collapses. Because the E2 page here, that's just the X group that I showed you earlier. And for degree reasons, we cannot have any differential here, so the right side just collapses. And this was the answer. So we can, now I'm restricting to ROC3 graded, and then we can pick out what the ROC3 graded elements from here, like this. And it's not important the precise formula is, but we can rewrite this as some group cohomology of some representation, and more specifically for these cases we have rho bar, and for these cases we have the trivial representation. And then we have some generators in those degrees using the expressions of these V1s and X. So this is the answer here, like this. And n goes from 0 to greater or equal to 0. Right, so that's this blue part. And previously we know what was the red part. It's like this. So now we can analyze this further. The homology, so this was already the homology, it's the sim. And this sim is known. It's some free part plus a symmetric algebra on this trivial representation denoted n rho bar. This n rho bar is the unique trivial representation in sim 3. And conceptually, you can think of it as the norm. It's a symmetric algebra on that, and then you have a rho bar, tensored with everything. And so you have this as non-frees, and you also know the number of frees. They are just I plus 1 over 3 in sim I. So here, on the right side, I said earlier, we have these group cohomologies and these generators. And on the left side, we have the answer from the previous page, and we can also write it as some group cohomologies with some generators. So this V bar is the norm. It spans the trivial representation. This alpha bar is the rho bar on the previous slide. So we want to know how it maps. Let me turn back a few slides to see where this is. So this is this map. We know what is this, we know what is this. If we know how it mapped, then we know what is this. So how do we figure this out? Well, we can assign some weight to each. Well, it's getting technical, but I think that's the sort of one of the fun parts. So I'm going to elaborate a little bit. we can assign weights to each representation, and then we have weights for all these generators as well. So the weight of this V bar becomes 3, and the weight of alpha bar is 1, and the weight of these elements on the right we also get. So we know the weight must match, so we know what elements map to what elements as representations, but we don't know precisely how. And to find how, we need to find a subcomplex of that weight that relates the two sides. So let me elaborate on the next page how. So let's look at this case where k is 6n, and the corresponding weight 6n elements are mu bar to the 2n and this mu 2n. And the question is, what is this map? Okay, so this mu 2n, we can analyze it. It comes from this mu 2n, because we computed by an x, so we know which element, which representation it comes from, and it comes from, let me think, some element in co-simplicial degree C6n. Sorry, it comes from some element in co-simplicial degree 4n, and that turns out to so that is this trivial representation 1 in degree co-simplicial degree 4n. So that's the place of where V2n come from. What about V bar 2n? Well, this comes from some homology of this cochain complex, and it's in co-simplicial degree 6n, and it's a trivial representation. And how are they related? Well, it's because this trivial representation here is not a cycle in this cochain complex. It maps to some row, some regular representation, which keeps mapping and terminates here as 1, and that one, terminates here as a row, and the homology of this, like this. I didn't write the maps, but you can imagine what they are. And the homology of this subcomplex is exactly this 1 that gives this V bar 2n. Right, so what happens when you compute group cohomology? This 1 gives you these diagonal F3s, and these rows give you these black dots. And then there are differentials going this way. So what do I mean? Well, this diagonal, they come from this 1, so they are the modules spanned by this V2n, and these black dots, they wouldn't exist in the good part. So in the good part, which is here, you just have all the diagonals. But in the overall thing, you have these black dots, so you have these differentials canceling these white dots with their companion, and then you end up starting from here, these ones, and from here, the V bar 2n, they so in the total thing, you only have elements starting from here. So from here to here, the map is that this element maps to A lambda over U lambda Vn times this element. And these elements don't exist in here because they are mapped by connecting homomorphism to some transfer elements. Okay, so to sum up, what we have deduced is that this is part of the coherent spectral sequence for the total thing, and the black dots are in the E infinity page of the evil thing, and these are the connecting homomorphism of the evil good sequence as well as the differentials in the coherent spectral sequence. So we want to, the point is that we want to deduce the E2. So we analyze everything here and here, so we can reverse engineer to know what's here, what's the E2 of this. The E2 is just all the dots here, and well, except for this one because it's a D1. And then all the differentials, you know, they're happening in the coherent spectral sequence. So that's a summary of what I just said, more precisely. So here, you have all these elements here. You also have the white dots on the previous page. You can precisely write down what they are. And then you have their companion, the black dots, which we denote by theta E, called evil classes, that receives the differential from theta in this spectral sequence. Okay, so that's the technical part. We deduced this and this. Now let's come back to this. So we computed it earlier. We have D1, D5, and D10. And the D1 actually fits in here as a 3-Box-like spectral sequence converging from this associated 3-adic associated gradient of pi star TMF2 to this pi star TMF2. So this actually commutes. So we can start this from E2 page, and then we have a D5 and D10. And now this is the E2 page. We have computed the bottom and the right, and using the bifiltration, we can deduce some differentials on the left. So it turns out that, so the right side, you have some differentials, theta hitting theta E's. Right, so if theta hits theta E here, and theta survives here, then here theta should also hit theta E. That's the first case. If theta hits theta E, Xi hits Xi E here, and theta hits Xi here, what happens is that on the left, theta E hits Xi E. So that's the two cases of differentials we deduce from these two. And after all this, it turns out that there are no more possible differentials. So we've finished this computation. And let me briefly show the answer for the integer graded part. All the differentials happen and collapse before the E12 page, so it collapses on the E12 page. And we recorded all surviving elements in this table. There are good classes, there are evil classes. And these evil classes, they will continue a 336 period pattern after this degree. And then there are also some copies of F3V0s. And these are also 336 periodic. And here, the number will grow as degree grows. And last but not least, we can get the sigma 3 equivariant part by taking the C2 fixed part of our computation. And the way is the following. So Lu and Krish, they computed sigma 3 equivariant cohomology of a point. And we can use the answer to deduce the C2 action on here. The answer is that A spoke sends to A spoke, U spoke to U spoke, U lambda to negative U lambda. And the two generators, in our case, V1 and X, they are sent to negative of them. So by taking fixed points on the previous slide, we can get the sigma 3 fixed points. And some remarks of what we observed in the computation. Number one, U lambda cubed is a permanent cycle. And we also computed the Z plus lambda and Z minus lambda graded part. So we have computed all the ROC3 graded part by this periodicity. And modulo some V0 towers, the sigma 3 fixed point is 32 periodic, just like you have for TMF. And also, modulo some V0 towers, it turns out that all elements on the E infinity page of our relative atom spectral sequence lie within a band of slope 1/4, as opposed to in atom spectral sequence of TMF2, because it's high 2, so you should have two bands. Okay, so let me finish by some more thoughts and comments on our project. So the highlight of our project is that we use this quotient of half algebraic mode transfer as input, and then using our bisynthetic filtration, we deduce all differentials from algebraic data, and there are no more differentials after that. And we can think of this TMF2 as a C3 analog of the C2 spectrum KUR, and you can play the same relative atom spectral sequence for KUR like this. And the homology here is a is a quotient half algebraic of the C2 equivariant Deuce-Inroth algebra. And it's denoted E2 star in a paper by Rika, and it's explicitly this. And Rika classified all C2 Deuce-Inroth algebra quotients as En star and An star. And we wonder, a project I really want to do, what are the all C3 equivariant Deuce-Inroth algebra quotients, and can we classify them? And this should be a first example to that. And also, this TMF2 is a C3 analog of the C2 spectrum, truncated Brown-Peterson spectrum BPR1. And because of this chromatic implication, this calculation TMF2 of C3 is closely related to the calculation of C3 homotopy fixed point of E2. And it would be nice if you can come up with some similar algebraic computation in general for EP-1 HCP. And a more wild dream is to have a model of E2N HC3 to the M for suitable N and M. But that's sort of a big dream. Okay, so that's all for my talk, and thank you for attending.
Thank you very much. So we have plenty of time for questions. Please, John.
So your calculation is basically an additive calculation of pi star of TMF rank 3.
Yes.
In the previous calculations, there were also some multiplicative calculations, but there was one multiplicative question that was left open. So if you take the class in UB 56 and look at the square, then there are two possible classes there. So do I get information about multiplicative questions like this?
We didn't think multiplicatively, but that's a good thing to consider.
Around page 40 or so, you didn't actually list the invariance, but I guess the problem is the beta 1 squared d cubed. If you square that, it's so in the atoms and relative atom spectral sequences, there's a possible filtration shift for that multiplication, which we were unable to decide. In case you're not, it's hard to see.
Yeah, so it's this 56?
Yeah, so the square of that could be, and there should also be something in 40. I'm sorry. Okay, well, sorry. But if you...
In 40, you mean this element?
Yes, so there's a periodicity element in degree 72 times
Yeah.
that element in degree 40, and that is some of the ambiguity in the square over there. So the question is really, is the square equal to that one you were pointing at, or is it that plus or minus the other one?
So our name here is just subjective, and we don't mean it's multiplicatively equal. So we didn't consider multiplicative.
Yeah, so I mean the name, so in ordinary modular form, well, okay, I think I'm being too detailed for this to be of general interest. Thanks.
Other questions? Okay, then we have a slightly longer coffee break than usual, and we thank Uli again.